Okay, hello everyone. I'm recording this video to go over how to find the phase constant for some of these waves problems. And like I said in class, this is just a math skill issue. Um, so I want to remind you two facts that are super important for this. So first of all, if you have a function doing whatever, it can look whatever, but there's a peak right at x equals 0. Okay, so this is f of x. And if you want to drag that, if you want to talk about the function that is the same thing, except it's shifted to the right a little bit. So notice how I tried to do that as best as I could. The red graph is the black graph shifted to the right. And let's say it shifted in amount A. So the peak there, which was at 0, was shifted to the right in amount A. So that graph is actually f of x minus A. Right? Because why is it minus even? So you shift the graph to the right, which is the positive x direction, and yet it's f of x minus A. So to kind of give at least one justification for why this might be the case, f has a maximum when its argument is 0. When its argument is 0. So in other words, f of 0 is equal to f max. And that's true no matter what. So if you look at the red graph, it's the same function, right? It's the same picture. It's the same graph. It's just displaced right or left. And that function achieves its maximum at x equals positive a, but notice how x equals positive a is when the argument is 0. So this argument is 0 when x equals positive a. Okay. So f of x minus a is displacing the graph to the right by an amount a. So that's one fact we're going to need a lot in finding this phase constant stuff. The other fact, so this is fact 1. The other fact, fact 2, has to do with trigonometric functions in particular. So let me draw a sine wave. Good enough. That's what a sine wave looks like. It's 0 and then it increases. So a sine wave, this is theta, and this is sine of theta. So remember that sine and cosine repeat every 2 pi radians. So this right here is theta equals 2 pi. And so if you want to shift this graph by a quarter cycle, a half cycle, etc., a half cycle, quarter cycle corresponds to a certain number of radians. When you're doing sine and cosine, every part of the sine and cosine is a certain number of radians. So this right here in particular, this is pi over 2 radians. So every quarter cycle. So in other words, you should think of a quarter cycle as being synonymous with pi over 2 radians. And a half cycle is synonymous with pi radians. And a full cycle is synonymous with 2 pi radians. Now, why am I going over this? Well, if this is sine of theta, and I want to actually plot, or I actually want to talk about the graph where, say, we go down right here, like this. What is the black graph in terms of sine theta? So is the black graph sine of theta plus or minus some amount, plus or minus pi over 2, etc.? Well, the point I was just emphasizing was, it looks like we said that a quarter cycle, which is how much we need to pick up the blue graph and shift it to the right a quarter of a cycle. You see how that's a quarter of a cycle. A quarter of a cycle, in terms of the argument of a trigonometric function, is pi over 2 radians. So the amount that we're shifting is pi over 2. And because we're shifting to the right, we're going to choose the minus sign. Okay, so the black graph is sine of theta minus pi over 2. Okay, and notice how if you plug in theta equals 0, you should get sine of negative pi over 2, which is -1, which is exactly where we are on this graph, right? So these two facts are all we need in order to solve for phase constants. So let's try and do some example problems based on. The figure to the graph is a snapshot graph at t equals 0, blah, blah, blah. Okay, wave speed, don't care about that. You can figure that out. Part B, what is the phase constant of this wave? Well, it depends on how we write the displacement equation for this wave. So we can write it in terms of sine or cosine. So let's do both, actually. So C1. So this almost looks like a sine, right? So I'm going to start off by saying, let's try C. Okay, C, assuming we're doing a sine wave. Okay, so the displacement D is going to be some amplitude, which the amplitude is 1 millimeter, but that's just kind of an aside. Doesn't really matter so much for shifting the graph. A sine kx plus or minus omega t. Now, remember that for a wave traveling in the negative x direction, we have to choose the plus sign right here. Okay, so it's going to be kx plus omega t means a wave moving in the negative x direction. And then the default is to just call this a positive phase constant. So the phase constant is positive if we shift the graph to the left, and the phase constant is negative if we shift the graph to the right. And this is just what we talked about here, right? That phase constant would be negative a if we're shifting the graph to the right. So here it looks like we're shifting the graph to the left, okay? But by how many radians? We have to figure out how much of a cycle have we shifted this thing to the right. So you have to think about, well, this is where the sine normally would be, and how much do we shift it to the left? Well, we shifted it an amount such that, okay, so let me draw a normal sine right here, and this is pi over 2 radians. Now we shifted it to the left an amount so that, see how it's exactly now halfway up. This is the displacement A, and this is 1/2 A is now where the graph is crossing the vertical axis. So where does this graph get have the value 1/2 A? It's not halfway, right? Halfway, this is like 1 over square root of 2 times the maximum amplitude. So the graph actually hits a maximum before that. And if you remember, it's at 30 degrees or pi over 6 radians when you get 1/2. So this is 1 for the sine. And you reach a value 1/2 at an angle pi over 6. So what this means is that we took a sine wave and we shifted it to the left an amount of phase that's equal to pi over 6. So here, pi is equal to pi over 6 if we chose the sine wave, right? Or, okay, so this is parts B and C, one solution. Another way of doing parts B and C is to say that the displacement is a cosine, the same kx and omega t, but now the phase constant is going to be different if we have a cosine instead of a sine. So if we started with a cosine, we're shifting the cosine. Remember, cosine normally looks like this. And we're shifting the cosine to the right some amount. And it looks like we're shifting the cosine to the right by 60 degrees. So because we're shifting to the right, the phase constant is negative, and 60 degrees is pi over 3 radians. Okay, so your answer for part B kind of depends on your answer for part C. If your answer for part C is a sine, then the phase constant is plus pi over 6. And for a cosine, it's going to be minus pi over 3. You can also add any integer multiple of 2 pi, and this is okay. So 2 pi times any integer is also a solution for these. But modulo that, the answer is unique. I mean, if you force your angle to be between 0 and 360 degrees, or between 0 and 2 pi, then I guess this one is okay. And then this one would be, instead of negative pi over 3, instead of negative 60 degrees, we would probably say that that's plus 300 degrees, or 5 pi over 3, or 5 pi over 3. Same thing, right? That's just adding in 2 pi to it. Okay. So, I mean, what that means is that you could start with a cosine, and if the phase constant you're forcing to be positive, that means you're telling the person that you have to move the graph to the left. So instead of moving it to the right 60 degrees, you can move it to the left 300 degrees. And it also produces the same graph. Okay. So this is a clicker question, and you can pause because you're experts now. So try this. So it looks like this graph crosses at 0.7. It's almost exactly 1 over square root of 2, which is exactly halfway between here and the maximum. So the amount by which this graph shifted from, say, a sine, which is the answer choices, looks like we took a sine and we shifted it to the left by half of a quarter cycle, or by 45 degrees, or by pi over 4 radians. So shifting to the left means plus, and pi over 4 radians. Okay. One last example for this video. To the left is a snapshot of a wave at t equals 1/2 times the period. Okay. So the graph in blue, I think that's blue and not purple. Let's call it blue. So this is 1/2 period. Where was the graph at t equals 0? Well, 1/2 period is easy because, okay, so here is where the graph looks like the y value is 0 and the slope dy dx is negative. And the next time that happens is right here. It looks like the wavelength is 4 meters. Okay, that's one full wave appears right there. And so what did the graph look like at t equals 0? Well, remember, this graph is moving to the left based on this information. The graph is moving to the left, so you have to kind of move it to the right. And a half a period corresponds to half a cycle, or in other words, pi radians. So if we pick up this graph and we move it to the right, a half a cycle, instead of looking like a minus sign, it's going to look like a plus sign. It's going to look like this. So the thing that I'm drawing in black is what the wave looks like. It's a snapshot at t equals 0. So at t equals 0, this wave just looks like a sine. So in terms of y equals a sine of, so it's going to be kx plus omega t, not, this has to be the plus because the wave is moving in the minus x direction, or to the left. So it's plus omega t. And then at t equals 0, we can ignore this. I'm going to cross it out and then take it back. But at t equals 0, I can ignore this. And we have sine kx that we don't want to move at all, right? At t equals 0, which is why we cross that out. At t equals 0, we just have a sine wave. And so the phase constant is actually 0 in this problem. Okay, so phi naught is equal to 0. So the answer is just y equals a sine kx plus omega t with no phase constant. That's what this graph corresponds to. So this is the y at any x and t. And in particular, what this means is that if you plug in, so if you look at y of x at t equals 1/2 t, let's see what happens when we plug that in. Let's verify that. Okay, so let me pause what I'm saying. The thing that I just wrote down is true for any x and for any time. So the super general form of the equation. And I just want to verify that we get this blue picture back if we plug in t as 1/2 a period. So if we plug in 1/2 a period, we get a sine kx plus omega times 1/2 of a period. Now, omega times 1/2 of a period, if you plug in for omega in terms of capital T or capital T in terms of omega, you'll see that that's exactly pi radians. Kx plus pi radians, which makes sense because half a period should correspond to a phase of half a cycle, which is pi radians. So you have y equals a sine of kx plus pi. So you have a sine and you've shifted it 180 degrees. And that's exactly what this matches the blue graph, which is great. That's a verification that our answer is okay. So our answer in black, which is it's describing at all positions at all times, looks like it matches the blue picture at t lowercase t equals 1/2 capital T. It should look like a minus sign. Notice how sine of kx plus um, pi. Notice how the blue graph is exactly minus the black graph. Like this is the minus function of this. So this is also minus a sine kx, which is exactly what the blue graph. Okay. Yay.